it's not the same direction.
Yeah, but even, you know, if you take these pictures of reconnection.
I have no reason to think that that's necessarily the case, but that's not a good argument.
Donc le projet BRAMS est un projet de détection et de caractérisation des météores qui rentrent dans notre atmosphère au moyen de techniques radio. Le principe est que quand un météore entre dans l'atmosphère, il laisse dans son sillage une traînée d'électrons sur laquelle une onde radio peut venir se réfléchir. Et dans certaines conditions, elle peut être captée au niveau du récepteur. Le principe du réseau BRAMS, c'est que nous avons un émetteur qui est situé à Dourbe, un émetteur dédié, qui émet un signal vers le ciel. Tout météore qui est illuminé par ce signal peut donner lieu à une réflexion et ce signal réfléchi peut être capté par notre antenne ici sur le site du cours. En analysant ce signal, on peut avoir de l'information sur l'objet qui a créé, sur le météoroïde lui-même, donc l'objet qui est rentré dans l'atmosphère. Le seul point important, c'est qu'on a de l'information que sur un point de la trajectoire. Donc afin de pouvoir retrouver les trajectoires des objets qui rentrent dans l'atmosphère, on a besoin d'un réseau de stations qui sont réparties sur tout le territoire belge. Et actuellement, nous avons 22 stations de réception. Donc un aspect important du réseau BRAMS, c'est qu'il s'agit d'une collaboration entre professionnels et amateurs, dans le sens où la plupart des stations de réception qui sont réparties sur le territoire belge sont en fait hébergées par des radioamateurs ou des groupes d'amateurs astronomes. Donc, pour citer un exemple concret, l'Eurospace Center à Redu héberge une de nos stations BRAMS. Voilà, c'est tout. Donc l'avantage des données radio, c'est qu'en fait, on peut observer de façon continue, 24 heures sur 24, et on ne dépend pas également des conditions météorologiques. Les données sont enregistrées en temps réel, comme on le voit ici. Ce qu'on voit ici, c'est de l'analyse des données. Donc le signal continu ici est en fait le signal qui provient de notre émetteur situé à Dourbe. Ces longues traces en forme de S sont en fait des réflexions sur des avions, donc pour nous ce sont des échos parasites. Et tous ces petits traits verticaux sont en fait des échos sur des météores. Donc en analysant des signaux reçus ici, on peut obtenir des informations sur l'objet qui a créé la traînée d'électrons.
The TOSCA project is a European cooperation that enables researchers from all around Europe to collaborate together in order to understand how our Sun influences the climate of our Earth. It is really important as we don't know exactly how much the humans have influenced our climate and how much the Sun is responsible for.
So at the side of Humain, we have an operating program that permits to operate the antenna. This program allows you to receive instructions from outside, so not manually done. So we have created a web interface. You can just say, put yourself at that position at that time, or you can say, track this object in the sky, which can be the Sun, but it can be another radio source. So the program also is designed for multiple antennas, so you can actually operate different antennas.
Okay, so here in this room is the Proba 2 Science Center, and here we command the two instruments on board of the ESA microsatellite Proba 2. The two instruments are this one. First SWAP is an EUV imager showing you the sun in its full wealth at 1 million Kelvin. And the second instrument is LIRA. LIRA is a radiometer which observes the irradiance of the sun in 4 different wavelengths. Here you see what LIRA has observed today, and so you can see here 2 flares which happened this morning.
Hi, I'm a team member of the B2SE operations team, and my job is to control, to check all the movies that we have, which come in from the SWAP instrument. So we can extract the interesting events and put them in a weekly report, for example, or put it on the website.
I send out the commands to the Proba 2 spacecraft, and I make sure that the data that is being beamed down gets processed properly. One of the things I have to make sure is that we do not do special operations inside the South Atlantic anomaly.
Here at the Solar-Terrestrial Center of Excellence, we are studying solar atmosphere with the help of new space solar missions like SOHO, SDO, Stereo, Hinode. So here I'm going to show an example of how we can determine the 3-dimensional configuration of coronal mass ejections. So here, these are 2 images taken by the SOHO spacecraft near the Earth of 2 halo CMEs. But we do not know if these CMEs are going towards the Earth or away from the Earth, which is important for space weather, because if a CME arrives at the Earth, it may produce a geomagnetic storm, for example. So with Stereo, which is a mission to study the Sun in 3 dimensions, consisting of 2 spacecraft, Stereo ahead and Stereo behind. And now the configuration of the 3 observation points is such that we can see the whole corona from all sides in 3 dimensions. We can disentangle the CMEs and distinguish the CMEs which are going towards the Earth from those which are going away from the Earth. So here is a movie from a coronagraph on Stereo A, which will show exactly the same 2 CMEs which appeared as halo from the Earth. This is the first one. It's going to the left, which means it goes towards the Earth. And the second CME, which we will see now here, it goes to the right, which means it goes away from the Earth. So the first CME could be geoeffective, but the second CME could not be geoeffective. So here at the Solar-Terrestrial Center of Excellence, we are producing studies of 3-dimensional configuration of CMEs and of their propagation in the heliosphere and their effect on the Earth.
So I will present what was happening during this week. That's the situation today. You see that we have 6 active regions numbered by Catania, and 3 of them are already going behind the lens. You see the magnetogram, which is mostly something particular. There is an active region here, this one, which becomes, let's say, quite good to produce sound layering. And there is an active region here, I will show the STCE network, which became much more complicated and even increase the surface area, although it's going towards the living.
With a technical operator and a scientific operator and either visitors walking in and out. There is no forecast to be heard. There is a scientific person who has to receive telephone calls and emails from a ticket system and answer them in real time or contact the appropriate expert.
I'm the STCE's technical operator, and I make sure that the systems run on a day-to-day basis by monitoring whether disks get full or stuff like that.
I'm one of the scientific operators at the STCE rooms, so it's an operation room where we take care that all different space weather products and ESA products running at the reduced station are running fine. We are also involved when users are having questions on space weather.
We have developed a three-dimensional dynamic model of the plasma sphere. That's the extension of the ionosphere at higher altitudes. It corresponds to cold particles with an energy around 1 electron volt. And when the geomagnetic activity increases, then the plasma pulse, the limit of the plasma sphere, this goes closer to the Earth, and the plasma sphere is eroded and the plasma sphere becomes smaller. The radiation belts are regions of the inner magnetosphere filled with very energetic electrons and protons from million electron volts, and it is also affected by geomagnetic activity. And when there is a geomagnetic storm, here shown by an inverted peak of the DST index, you can see that there is an increase of the flux, especially here in the outer belt located above 2 or 3 Earth radii.
De fixer la bride. Donc oui, ça va se mettre. Mais je vais vous montrer sur le...
So our job at the Royal Observatory of Belgium, in the GNSS team, is to monitor the ionosphere in real time. So what is important to monitor the ionosphere is because this layer of the atmosphere interacts with radio waves like electromagnetic waves. So these are the waves which are used for navigation, for example, for GPS, and all the GNSS systems, but also when you want to communicate between one continent with another continent, use the reflection of the signals on this ionosphere. And this propagation of the signals is strongly dependent on the ionospheric activity. And one of the main parameters which can be estimated over Europe in near time using the GPS station, a network of 250 stations. This parameter of the ionosphere is the total electron content, so which reflects the number of free electrons in the ionosphere. And depending on this quantity of electrons on the ionosphere, you will have some disturbance or not on radio wave propagations. So that's what we are doing now at the observatory, is to estimate this total electron content in real time each 15 minutes. And we can have some here pictures of the ionospheric activity for this day, so today, 27 December, 27.
Moet iets van 38 jaar gedaan of zo. Ja. Daniel. Nee. Met binden, warm blijven. Je hebt hier ook die batterijen.
Een beetje meest. Ja, het is niet allemaal weg. Nee.
In Antwerp, Belgium, a satellite the size of a washing machine is being built. This mini-satellite, Proba 2, is due for launch in 2009 as a secondary satellite in the SMOS Earth Observation Mission. It'll weigh between 120 and 150 kilos, and being small has particular advantages. They may be small, but the Proba satellites are highly sophisticated devices that are effectively made to measure.
Low-cost missions allow small companies access to space and provide them with necessary experience to study the behavior of the Sun. The space weather interferes with telecommunications and electrical power on Earth.
Containers being unloaded from the aircraft. This is the container which is specially designed. It's an environmental chamber for the SMOS satellite, and together with its ground support equipment it goes by rail from Arkhangelsk to Rings.
And here comes Proba 2.
Yes, indeed. What we see here on the screen is the separation adapter for Proba 2.
Yes, you can see the very specialized handling equipment which they have to... And subsequently here you see SMOS being lowered very carefully with the cone over the top of the Proba space. And shortly thereafter they maneuver the upper composite and the shell of the... This is the finished product. It's the upper composite.
With its 130 kilos, the Proba 2 satellite is less than 1 cubic meter in size. On board, 17 new technological developments.
Our mission is to be...
This is the Redu satellite tracking station in the Belgian Ardennes. It's the control center of the mission Proba.
Because of its fundamental importance to our existence, the Sun is a critically important subject for scientific study. Solar Orbiter, an ESA mission in collaboration with NASA, has the objective of sending a spacecraft to monitor and observe the Sun, using a suite of advanced scientific instruments and at a proximity never before achieved. Scientists hope to learn more about our home star, and in doing so, usher in the next era in solar science.
Protocols and you have to change whatever you want to, but detect it when you...
After separation from the American Atlas launch vehicle, the Solar Orbiter spacecraft will travel along a highly inclined escape trajectory on course for the planet Venus. During the few months between Earth and Venus, the Solar Orbiter spacecraft will deploy and check out the instruments and subsystems required to complete the mission successfully. Each one is designed to alter the trajectory of the spacecraft to target the next planet in the sequence, gradually reducing the orbital energy of the spacecraft and bringing it closer and closer to the Sun. During the operational orbit, the in-situ instrumentation will be permanently active. At its closest approach to the Sun, Solar Orbiter will encounter almost 13 times the solar flux received at the Earth, necessitating the presence of the heat shield on the spacecraft. The heat shield relies on being able to reject heat to cold space via the gap between the layers. However, it is not possible to keep every part of the spacecraft behind the heat shield. The solar arrays must be exposed to the Sun, and the high-gain antenna must sit in the sunlight in order to access the widely varying Earth positions. Accordingly, Solar Orbiter must manage the temperature of these critical items to ensure their survival as the distance to the Sun varies. Solar Orbiter is an advanced mission in the best traditions of European science, using a pragmatic blend of existing and new technologies to achieve the mission's scientific objectives. The vantage point offered by the spacecraft trajectory will be unique, encompassing both near-Sun and high-latitude views, and the combination of remote sensing and in-situ measurements promises to revolutionize our understanding of the Sun.